According to Asger Aaboe, the origins of Western astronomy can be found in Mesopotamia, and all Western efforts in the exact sciences are descendants in direct line from the work of the late Babylonian astronomers. Our knowledge of Sumerian astronomy is indirect, via the earliest Babylonian star catalogues dating from about 1200 BCE. The fact that many star names appear in Sumerian suggests a continuity reaching into the early Bronze Age. The history of astronomy in Mesopotamia and the world begins with the Sumerians, who developed the earliest writing system, known as cuneiform, around 3500–3200 BC. The Sumerians developed a form of astronomy that had an important influence on the sophisticated astronomy of the Babylonians. Astrology, which gave planetary gods an important role in Mesopotamian mythology and religion, began with the Sumerians. They also used a sexagesimal place value number system, which simplified the task of recording very great and very small numbers. The modern practice of dividing a circle into 360 degrees, of 60 minutes each hour, began with the Sumerians. During the 8th and 7th centuries BCE, Babylonian astronomers developed a new empirical approach to astronomy. They began studying philosophy dealing with the ideal nature of the universe and began employing an internal logic within their predictive planetary systems. This was an important contribution to astronomy and the philosophy of science, and some scholars have thus referred to this new approach as the first scientific revolution. This new approach to astronomy was adopted and further developed in Greek and Hellenistic astronomy. Classical Greek and Latin sources frequently use the term Chaldeans for the astronomers of Mesopotamia, who were, in reality, priest-scribes specializing in astrology and other forms of divination. Only fragments of Babylonian astronomy have survived, consisting largely of contemporary clay tablets with ephemerides and procedure texts. Hence current knowledge of Babylonian planetary theory is in a fragmentary state. Nevertheless, the surviving fragments show that, according to the historian Aaboe, Babylonian astronomy was the first and highly successful attempt at giving a refined mathematical description of astronomical phenomena, and that all subsequent varieties of scientific astronomy, in the Hellenistic world, in India, in Islam, and in the West, if not indeed all subsequent endeavor in the exact sciences, depend upon Babylonian astronomy in decisive and fundamental ways. Old Babylonian astronomy. Old Babylonian astronomy refers to the astronomy that was practiced during and after the First Babylonian dynasty and before the Neo-Babylonian Empire. The Babylonians were the first to recognize that astronomical phenomena are periodic and apply mathematics to their predictions. Tablets dating back to the Old Babylonian period documents the application of mathematics to the variation in the length of daylight over a solar year. Centuries of Babylonian observations of celestial phenomena are recorded in the series of cuneiform tablets known as the Enuma-Anu-Enlil. The oldest significant astronomical text that we possess is Tablet 63 of the Enuma-Anu-Enlil. The Venus Tablet of Ammisaduqa, which lists the first and last visible risings of Venus over a period of about 21 years. It is the earliest evidence that planetary phenomena were recognized as periodic. The Mul-Apan contains catalogues of stars and constellations as well as schemes for predicting heliacal risings and settings of the planets, and lengths of daylight as measured by a water clock, gnomon, shadows, and intercalations. The Babylonian Gu text arranges stars in strings that lie along declination circles and thus measure right ascensions or time intervals, and also employs the stars of the zenith, which are also separated by given right ascensional differences. There are dozens of cuneiform Mesopotamian texts with real observations of eclipses, mainly from Babylonia. Planetary theory. The Babylonians were the first civilization known to possess a functional theory of the planets. The oldest surviving planetary astronomical text is the Babylonian Venus tablet of Ammisaduqa, a 7th century BC copy of a list of observations of the motions of the planet Venus that probably dates as early as the 2nd millennium BC. The Babylonian astrologers also laid the foundations of what would eventually become Western astrology. The Enuma Anu Enlil, written during the Neo-Assyrian period in the 7th century BC, comprises a list of omens and their relationships with various celestial phenomena including the motions of the planets. Cosmology in contrast to the worldview presented in Mesopotamian and Assyro-Babylonian literature, particularly in Mesopotamian and Babylonian mythology. Very little is known about the cosmology and worldview of the ancient Babylonian astrologers and astronomers. This is largely due to the current fragmentary state of Babylonian planetary theory, and also due to Babylonian astronomy being independent from cosmology at the time. Nevertheless, traces of cosmology can be found in Babylonian literature and mythology. In Babylonian cosmology, the earth and the heavens were depicted as a spatial whole, even one of round shape, with references to the circumference of heaven and earth, and the totality of heaven and earth. Their worldview was not exactly geocentric either. The idea of geocentrism, where the center of the earth is the exact center of the universe, did not yet exist in Babylonian cosmology, but was established later by the Greek philosopher Aristotle on the heavens. In contrast, Babylonian cosmology suggested that the cosmos revolved around circularly, with the heavens and the earth being equal and joined as a whole. The Babylonians and their predecessors, the Sumerians, also believed in a plurality of heavens and earths. This idea dates back to Sumerian incantations of the 2nd millennium BC, which refers to there being 7 heavens and 7 earths, linked possibly chronologically to the creation by 7 generations of gods. Neo-Babylonian Astronomy. Neo-Babylonian astronomy refers to the astronomy developed by Chaldean astronomers during the Neo-Babylonian, Achaemenid, Seleucid, and Parthian periods of Mesopotamian history. A significant increase in the quality and frequency of Babylonian observations appeared during the reign of Nabonassar. The systematic records of ominous phenomena in Babylonian astronomical diaries that began at this time allowed for the discovery of a repeating 18-year Saros cycle of lunar eclipses. For example, the Greco-Egyptian astronomer Ptolemy later used Nabonassar's reign to fix the beginning of an era, since he felt that the earliest usable observations began at this time. The last stages in the development of Babylonian astronomy took place during the time of the Seleucid Empire. In the 3rd century BC, astronomers began to use goal-year texts to predict the motions of the planets. These texts compiled records of past observations to find repeating occurrences of ominous phenomena for each planet. About the same time, or shortly afterwards, astronomers created mathematical models that allowed them to predict these phenomena directly, without consulting past records. Arithmetical predictions. Though there is a lack of surviving material on Babylonian planetary theory, it appears most of the Chaldean astronomers were concerned mainly with ephemerides and not with theory. Most of the predictive Babylonian planetary models that have survived were usually strictly empirical and arithmetical, and usually did not involve geometry, cosmology, or speculative philosophy like that of the later Hellenistic models. Though the Babylonian astronomers were concerned with the philosophy dealing with the ideal nature of the early universe. In contrast to Greek astronomy, which was dependent upon cosmology, Babylonian astronomy was independent from cosmology, whereas Greek astronomers expressed prejudice in favor of circles or spheres rotating with uniform motion. Such a preference did not exist for Babylonian astronomers, for whom uniform circular motion was never a requirement for planetary orbits. There is no evidence that the celestial bodies moved in uniform circular motion, or along celestial spheres, in Babylonian astronomy. Contributions made by the Chaldean astronomers during this period include the discovery of eclipse cycles and Saros cycles, and many accurate astronomical observations. For example, they observed that the Sun's motion along the ecliptic was not uniform. Though they were unaware of why this was, it is today known that this is due to the Earth moving in an elliptic orbit around the Sun, with the Earth moving swifter when it is nearer to the Sun at perihelion and moving slower when it is farther away at aphelion. Chaldean astronomers known to have followed this model include Naburi Manu, Kidinu, Berosus, and Sudenes. They are known to have had a significant influence on the Greek astronomer Hipparchus and the Egyptian astronomer Ptolemy, as well as other Hellenistic astronomers. Heliocentric astronomy. The only surviving planetary model from among the Chaldean astronomers is that of Seleucus of Seleucia, who supported Aristarchus of Samos' heliocentric model. Seleucus is known from the writings of Plutarch, Aetius, Strabo, and Muhammad ibn Zakaria al-Razi. Strabo lists Seleucus as one of the foremost influential Chaldean, Babylonian astronomers, alongside Kidinus, Naburianos, and Sudenes. Their works were originally written in the Akkadian language and later translated into Greek. Seleucus, however, was unique among them in that he was the only one known to have supported the heliocentric theory of planetary motion proposed by Aristarchus, where the Earth rotated around its own axis which in turn revolved around the Sun. According to Plutarch, Seleucus even proved the heliocentric system through reasoning, though it is not known what arguments he used. According to Lucia Russo, his arguments were probably related to the phenomenon of tides. Seleucus correctly theorized that tides were caused by the Moon, although he believed that the interaction was mediated by the Earth's atmosphere. He noted that the tides varied in time and strength in different parts of the world. According to Strabo, Seleucus was the first to state that the tides are due to the attraction of the Moon, and that the height of the tides depends on the Moon's position relative to the Sun. According to Bartholindert van der Weyden, Seleucus may have proved the heliocentric theory by determining the constants of a geometric model for the heliocentric theory and by developing methods to compute planetary positions using this model. He may have used trigonometric methods that were available in his time, as he was a contemporary of Hipparchus. None of his original writings or Greek translations have survived, though a fragment of his work has survived only in Arabic translation, which was later referred to by the Persian philosopher Muhammad ibn Zakaria al-Razi. Babylonian influence on Hellenistic astronomy. Many of the works of ancient Greek and Hellenistic writers have been preserved up to the present time, or some aspects of their work and thought are still known through later references. However, achievements in these fields by earlier ancient Near Eastern civilizations, notably those in Babylonia, were forgotten for a long time. Since the discovery of key archaeological sites in the 19th century, many cuneiform writings on clay tablets have been found, some of them related to astronomy. Most known astronomical tablets have been described by Abraham Sachs and later published by Otto Neubauer in the Astronomical Cuneiform Texts. Since the rediscovery of the Babylonian civilization, it has become apparent that Hellenistic astronomy was strongly influenced by the Chaldeans. The best documented borrowings are those of Hipparchus and Claudius Ptolemy. Early influence. Many scholars agree that the Metonic cycle is likely to have been learned by the Greeks from Babylonian scribes. Meton of Athens, a Greek astronomer of the 5th century BCE, developed a lunisolar calendar based on the fact that 19 solar years is about equal to 235 lunar months, a period relation already known to the Babylonians. In the 4th century, Eudoxus of Cnidus wrote a book on the fixed stars. His descriptions of many constellations, especially the 12 signs of the zodiac, are suspiciously similar to Babylonian originals. The following century Aristarchus of Samos used an eclipse cycle of Babylonian origin called the Saros cycle to determine the year length. However, all these examples of early influence must be inferred and the chain of transmission is not known. Influence on Hipparchus and Ptolemy in 1900. Franz Xaver Kugler demonstrated that Ptolemy had stated in his Almagest IV-2 that Hipparchus improved the values for the moon's periods known to him from even more ancient astronomers by comparing eclipse observations made earlier by the Chaldeans and by himself. However, Kugler found that the periods that Ptolemy attributes to Hipparchus had already been used in Babylonian ephemerides, specifically the collection of texts nowadays called System B. Apparently, Hipparchus only confirmed the validity of the periods he learned from the Chaldeans by his newer observations. Later Greek knowledge of this specific Babylonian theory is confirmed by 2nd century papyrus, which contains 32 lines of a single column of calculations for the moon using this same System B, but written in Greek on papyrus rather than in cuneiform on clay tablets. It is clear that Hipparchus had an essentially complete list of eclipse observations covering many centuries. Most likely these had been compiled from their diary tablets. These are clay tablets recording all relevant observations that the Chaldeans routinely made. Preserved examples date from 652 BC to AD 130, but probably the records went back as far as the reign of the Babylonian king Nabonassar. Ptolemy starts his chronology with the first day in the Egyptian calendar of the first year of Nabonassar, i.e., the 26th of February 747 BC. This raw material by itself must have been tough to use, and no doubt the Chaldeans themselves compiled extracts of e.g., all observed eclipses. This allowed them to recognize periodic recurrences of events. Among others they used in System B. 223 months equals 239 returns in anomaly equals 242 returns in latitude. This is now known as the Saros period, which is very useful for predicting eclipses. 251 months equals 269 returns in anomaly. 5,458 months equals 5,923 returns in latitude. One synodic month equals 29,31500820 days. The Babylonians expressed all periods in synodic months, probably because they used a lunisolar calendar. Various relations with yearly phenomena led to different values for the length of the year. Similarly, various relations between the periods of the planets were known. The relations that Ptolemy attributes to Hipparchus in Almagest IX-3 had all already been used in predictions found on Babylonian clay tablets. Other traces of Babylonian practice in Hipparchus are work of first Greek known to divide the circle in 360 degrees of 60 arc minutes. First, consistent use of the sexagesimal number system. The use of the unit pecus of about 2 degrees or 2.5 degrees. Use of a short period of 248 days equals 9 anomalistic months. Means of transmission. All this knowledge was transferred to the Greeks probably shortly after the conquest by Alexander the Great. According to the late classical philosopher Simplicius, Alexander ordered the translation of the historical astronomical records under supervision of his chronicler Callisthenes of Olynthus, who sent it to his uncle Aristotle. It is worth mentioning here that although Simplicius is a very late source, his account may be reliable. He spent some time in exile at the Sassanid court, and may have accessed sources otherwise lost in the West. It is striking that he mentions the title Theresis, which is an odd name for a historical work, but is in fact an adequate translation of the Babylonian title Masatu, meaning guarding, but also observing. Anyway, Aristotle's pupil Callippus of Cyzicus introduced to his 76-year cycle, which improved upon the 19-year Metonic cycle, about that time. He had the first year of his first cycle start at the summer solstice of the 28th of June 330 BC, but later he seems to have counted lunar months from the first month after Alexander's decisive battle at Gaugamela in fall 331 BC. So Callippus may have obtained his data from Babylonian sources and his calendar may have been anticipated by Kidanu. Also it is known that the Babylonian priest known as Berosus wrote around 281 BC a book in Greek on the history of Babylonia, the Babylonica. For the new ruler Antiochus I, it is said that later he founded a school of astrology on the Greek island of Kos. Another candidate for teaching the Greeks about Babylonian astrology was Pseudenes, who was at the court of Italus Isota late in the 3rd century BC. In any case, the translation of the astronomical records required profound knowledge of the cuneiform script, the language, and the procedures. So it seems likely that it was done by some unidentified Chaldeans. Now, the Babylonians dated their observations in their lunisolar calendar, in which months and years have varying lengths. At the time they did not use a regular calendar, but started a new month based on observations of the new moon. This made it very tedious to compute the time interval between events. What Hipparchus may have done is transform these records to the Egyptian calendar, which uses a fixed year of always 365 days. This makes computing time intervals much easier. Ptolemy dated all observations in this calendar. He also writes that all that he did was to make a compilation of the planetary observations arranged in a more useful way. Pliny states, on eclipse predictions, after their time the courses of both stars for 600 years were prophesied by Hipparchus. This seems to imply that Hipparchus predicted eclipses for a period of 600 years, but considering the enormous amount of computation required, this is very unlikely. Rather, Hipparchus would have made a list of all eclipses from Nabonidus' time to his own.